Centripetal acceleration was again the topic of today's class. Specifically, what that means with regard to the centripetal force. Okay, remember, we're dealing with angular variables now. We're dealing with motion on a circle. So you have some particle, or person, or something that is moving from point, say A here, to point B up here. And it's describing an arc along of a circle with a constant radius. So some radius r right there. So it has gone through an angle of delta theta for its displacement, and it has had an angular velocity, well, it does have an angular velocity in that time, to get it from there to there, and an angular acceleration, alpha. So we have delta theta, we have omega, and we have alpha. Those being the angular quantities that are similar to the linear quantities, and as we mentioned last time, well, as I mentioned last time, you can talk about the relationship between theta, omega, alpha, and time, just like you would think about that for x, v, a, and time, with regard to motion under constant acceleration, as long as you're experiencing a constant angular acceleration. So, then, if you're thinking about the tangential relationships for what's going on, we know that the tangential velocity is equal to r times the angular velocity, and the tangential acceleration is equal to r times the angular acceleration. So the r, again, that radius, which I called capital R, being the constant quantity in the situation, since we're talking about motion constrained to being on a circle. So these are the tangential values. However, there is an acceleration that ends up being pointed towards the center, and that's the centripetal acceleration. So the word centripetal means center seeking. And so the centripetal acceleration of an object, something that is being forced to move in a circle, is directed towards the center by whatever is causing it to move in that circle. So, if, take for example my keys that are on the end of this string, okay, if I move them in a circle, okay, the reason that they are there and moving and constrained to being on that circle is because of the tension that is actually in this string. Okay? Doesn't matter, I mean, the values are slightly different because gravity is involved here. If I move it in a horizontal circle, it's still moving in a circle, and the reason that it is doing that is because of the fact that it is connected to the string, and the string is moving. But the tension would therefore be the force that is actually making it stay in that circle. You have some acceleration that is constantly changing the behavior of this object. Okay? The object would want to be moving, if we're talking about it being right here at point B, would want to keep moving in a straight line. If there is no net force acting on this object, it will be moving in a straight line. However, there is a net force if it's constrained to move on this circle. Say we're talking about these keys, and we're talking about a string. Let me actually erase this from the center of the circle here. Let's say that this object is indeed my keys, and this would be the string. And I am moving it so that the string is keeping the keys moving in a circle. The keys would want to fly off in a straight direction, and in fact they would if I were to let go. They would move in a straight line with the velocity they had at that point. So if all of a sudden the string broke at this section of the motion of the keys, they would move in a straight line this way. Of course, under gravity, the influence of gravitational acceleration, they would describe a parabola with their projectile motion, as the keys did as they flew across the room. But that is what is happening. So the only reason they are moving in the circle is because of some force that is constantly changing the acceleration, constantly changing the velocity of this object, which would be the keys in this case. And it's not changing the speed, it's actually only changing the direction. So the acceleration is not anywhere at all lined up with the velocity vector. The velocity vector at that point is always perpendicular to the acceleration, so it cannot change the speed. However, that perpendicular nature means that it is constantly changing the direction. So the velocity of the object is pointed this way, the force says no, you're actually going to be instead coming more towards the center, so the direction changes so that it's bent more towards the center, until at the very top, it's now, instead of having any angle at all, it's going to be completely horizontal. And that will continue moving on around the circle because of the fact that it is experiencing some force that is making it change direction and tug back towards the center. So it has some resulting centripetal acceleration because of some force that's acting on it. And I wanted to emphasize that word resulting. Okay? It is a resultant force. The centripetal force you're talking about here is a resultant force of whatever is actually causing the force. So if we have sum of the forces is equal to ma with regard to Newton's second law, where this also is the cause and this is the effect, or these are the things which influence an object's behavior, and this is the resulting behavior of the object because of these forces that are acting on it. The centripetal acceleration is never involved on this side of the equation. If you're adding up all the forces that are acting on an object, the centripetal acceleration is not one of the forces that is causing the behavior. It is instead the resulting behavior the object is experiencing. Okay? So, if this is, we're talking about the keys here, and we're talking about the string, and let's think that we're just thinking about this horizontally and not thinking about this in terms of a vertical motion, but instead a horizontal circle, then the force that's relevant here is the tension force, which is directed towards the center. So that would be the force that goes on this side, the tension. And then the resulting behavior is going to be equal to the mass times the centripetal acceleration the object experiences. Okay? And that centripetal acceleration, as I derived in class by looking at self-similar triangles with regard to the motion around the circle and the fact that the magnitude of the velocity stays constant, the speed of the behavior, the speed of the key stays constant, then we know that the acceleration centripetally is equal to that tangential velocity squared divided by the radius. Or, if we use the fact that Vt is equal to r omega, which I just erased, then that means it also equals omega squared r. Okay. So, the tension set up in this string that's attached to my keys is creating the motion of the object in the circle, which is then also making it move at a certain speed. So if I know how long my string is, that would be the radius. So under here, I would put the tension directed towards the center is equal to the mass of my keys times their acceleration they're experiencing towards the center, which would be equal to the mvt squared over r. Okay. So I would know how fast they're moving if I know what the tension in my string is, and if I know the mass of the keys and the radius of how long the actual string is, which is the radius of the circle, which will be constant if we're talking about a circular motion. Okay. So notice I said the tension in the direction of the center is equal to the force the resultant force that I was experiencing directed towards the center. Remember, we always have to think about directions for what's going on here, and the tension is towards the center here, and the acceleration we're talking about is going to be towards the center seeking, and so they're on the same direction. So yes, we do have to worry about where in the circle we're talking about. So we talked in class about an example with a roller coaster and with a Ferris wheel. And let's just look at that quickly now to see what's going on. If we have a roller coaster, and a loop of a roller coaster, I should say, so we have a car coming in this way and we'll end up going out that way, okay? As it goes to the top, what are the forces that are actually acting on the roller coaster? The forces acting on the roller coaster are the force of gravity, which is pointed down, and the normal force from the track, which is also pointed down. Because again, the normal force is the contact force that is pushing on the car because the track is pushing on it. So because it is in contact with the track, it experiences that normal force. So you have these two forces, and there are no other forces involved, and those two forces together make it move on the circle. So at the top, we have the sum of our forces is equal to mass times acceleration, right? And we have both the n and the gravitational force pointed downwards. Minus n minus mg is equal to the resulting behavior, which is the centripetal acceleration, right? Times the mass, of course, because it's constrained to move in a circle by the track. So that will have a direction that's negative because we're going towards the center. So that is equal to negative m AC. Okay. Notice I did not draw the centripetal force in this free body diagram for the for the roller coaster car, because it's not there. It's the resulting behavior. It's not the actual behavior that's making it move in a circle. It's how you describe the resulting behavior. So, canceling out the negatives, the centripetal acceleration is going to be the additive combination of the normal force and the gravitational force. Now, if we're at the bottom for this roller coaster, then we have the gravitational force pointed downward, and we have the normal force from the track pushing up, because of the relationship for how the car is actually laying on the track right here. So then we have positive n minus mg is equal to positive m AC. So now, instead of the acceleration being the addition of those two forces divided by the mass, it's now the subtraction of the two forces divided by the mass. And then if we're looking at it sometime halfway around the trip, let's say we're over here, okay, then what are the forces acting on it this way? You have the gravitational force, which is pulling it downward, and you have the normal force from the track. And so, in order to look at what the actual centripetal acceleration is being caused by, you can only look at the forces that are actually directed towards the center, because that's the direction where the centripetal acceleration is directed. So the sum of our forces in this case is only the normal force. So you have n, and directed in the rightward direction, which we'll call positive for a usual convention for positive x. So positive n would then be equal to our acceleration. Now it does have some other acceleration in this direction, going downward, and so the resultant acceleration that the keys are experiencing in this case is going to be the acceleration you have from the gravitational force going downward and the acceleration of the centripetal force going inward. So these two things are perpendicular, and so the overall acceleration this would experience would be simply the Pythagorean theorem applied to these two different accelerations. Okay. But the basic idea is that the centripetal acceleration, which is a resultant behavior of the forces acting on the object, okay, is always directed towards the center. So if we're looking at this one that's halfway, the gravitational force is not involved if we're thinking about the acceleration, the centripetal acceleration, because it's not directed towards the center. Okay. So knowing this, then we could always say what's the velocity, or what's the angular velocity, since we know that AC is equal to v squared over r, or omega squared r. Okay, so we need to use our knowledge of Newton's second law, and use our knowledge now of the angular quantities in order to figure out what's going on with this constant circular motion.